Hi, my name is Pankaj Kumar Pandit. In this video, we will deep dive into binary search. I have listed four things which I am going to explain this thing in this video. So let's start with linear search. Okay, so linear search. Let's start with what is the problem statement. The problem says that we have given a sorted list. Okay, let's suppose we have given sorted list 4, 6, 8, 9, and 10. This is the list we have given, and we also given a target value. Let's say in this case target is 9, and we have to return true if this target present in the list. Then we have to return true, otherwise return false. As you can see, 9 is present in the list, so we will just return true. How we are going to do that in a programming, like we will go to each and every element and we will compare it with the target element. If it is found, then we will return true. If it is not found, then we will return false. And if it is not found, then we will compare till the end of the list. Okay, so what is the time complexity it will taking? Like what when you talking about the time complexity is equal to the number of comparisons you have done. Like in this case, you have done for each and every element in the case of not present. In the case of not present uh, in the list. This is the worst case. Okay, worst case means let's say you have target is 13, and as you can see 13 is not present in the list, so you will start from the very starting point of the list, and you compare each and every element till the end. So you'll just comparing big O of n is the size of list. So this is the time complexity it will taking, which is very huge time complexity, and we have to reduce this time complexity. Remember one thing, we have also given this list is sorted and we are not utilizing this word. Like we have given a sorted list where we are utilizing it. So let's start with topic is optimization. It's optimization version, like and that's why the binary search, because we are given a sorted list, and we have to find the target element present in this list or not. So let's start. Okay, we will come the time complexity later of binary search. So let's say we are given a list, let's say A. This is the list we have given, let's say 4, 8, 10, 12, and 14. Okay, as you can see, this is the sorted list, and let's say target we are given equal to 12. Okay, in a binary search, what we will do, we will take two pointers, like let's say I am marking with the red. We have two pointer that is pointing low, and second one is high. Low pointer is pointing to the very first index of the array, like 0, 1, 2, 3, 4. Okay, this is the index I am marked down. So low is pointing to the very first index. Okay, high is pointing to the very last index of the element. Okay, in binary search we always calculate the mid. And how we are going to calculate? So mid is going to be low plus high divided by 2. Okay, what is low? Low is 0. What is high? High is 4, and divide by 2, it will be 2. So this is the mid. This is mid. Okay. Okay. After calculating mid, what we will do? We will compare that mid value with our target value. Like in this case, our mid value is 10. Now we will compare this. We have to consider two or three things, let's say. Okay, so first thing, uh, if my array of mid is equal to target. So as I said, like we always calculate, every time we will just calculate the mid. Okay, after calculating mid, that mid value, whatever the mid value present, we will compare that with the target value. Okay, and if the target value is equal, that means we found the target element in the list, so we will return true. This is one case. Okay, let's say in this case this is not true, like if you compare 10 or 12, they are not equal, so this condition is not true. Now what we will do, like we will do like because it is sorted, let's say 10 is this and 12 is this, which one is greater? Target is greater. What do you think, like 10? And if you see, like before this, before the 10 element, like this half, what you are seeing like 4 8 10, that means uh, previous, its left half, this is the left half, and I am saying that its left half contains less than 10 values, always less than 10, less than or equal to 10. Because it is sorted, its left half, this left half contains only values 10 or less than 10. Okay, that means we are sure, I am sure that here my target element is not present. Okay, if you finding the target element as a 12, you won't able to find 12 over here, because their elements are present 10 or less than 10. So where we will able to find the possibility of finding the target element. Okay, the possibility of finding the target element is here. So we don't need, now I am sure we don't require these three elements, so I'll just cancel it. My low, now I will take that low and pointing to here. Okay, so let's just keep the thing simple. So let me do all the things over here. Okay, so A would be what is that? 4 8 10 12. Okay, 4 8 10 12, and what was that is 14. Okay, let's do indexing as well. 0 1 2 3 and 4. Okay, so let's take a pointer. So this is the low and this is the high, and what is the mid? This is the mid. Okay, let's mark it with a green color so that you can see that. Okay, now I'm saying that it's left half. So this is the left half. This left half do not contain any target value, because my target value is greater. So it is greater, that means I'm sure if the element, if my target is present in this array, then it will present on the right side. So this is the right side, and this is the left side. Okay, so how I will eliminate this left side? Simply, I'll just move the low pointer to the mid plus 1. So now our array look like this. Let me take, this is 4, 8, 10, 12, and 14. Now my pointers are, my high is as it is. Now my low is pointing to here. Okay, so 0, 1, 2, 3, 4. Okay, so my low is now pointing to the 3. Okay, now my search space is this thing. You can just leave this like in your head, just forget it about. Like now you can zoom it. So we have 12 and 14 remaining. Now index is 3 and 4. Now low is pointing to here and my high is pointing to here. Now I'll just apply the same thing, like calculate the mid. How? So mid will be mid equal to low plus high divided by 2. What is low? 3 plus high. High is 4 divided by 2. 7 divided by 2. And remember always we will take the floor. Okay. So the 7 divided by 2 is 3. So now our mid is pointing to this thing. Now mid is pointing to this one. So mid and low pointing to the same thing. Now we will compare this mid value with target value, or mid value. What is the mid value is? Mid value is 12, and what is the target value? Target value is also 12. So here we will just return true, true. That's it. This is the binary search. Let me take another example so that you can understand better. So let's start. Let me write it example 2. Okay. So let's take an array. Let's say 12, 16, 18, and 56, 99. Okay. This is our array. Let's do indexing 0, 1, 2, 3, and 4. Let's say the target would be 99. Okay, so our low pointer is pointing to the very zeroth index, you can say, or starting element of the list, and high pointer is pointing to the last element or last index. Okay, every time what we will do, we will calculate the mid, and what will be the mid? 0. Low plus high divided by 2, 0 plus 4 divided by 2, that is 2. So this is our mid. Mark it and compare this mid value with the target. Now compare this. Now our target is 99 and our mid is 18. Which one is greater? Our target is greater. That means if our target present in this list, then it will be possible in the right side, not the left side. Right side. Okay, so we will reduce our search space. By the way, this is whole array is called search space. So I'm just saying this is left search space, and this is the right search space. We will just cancel it out. Okay, because we are sure that our target value is never present in the left side, because our mid value is 18 and our target value is 99. That means 99 is greater than 18, and whatever the left side is left value has, it is always greater than or less than or equal to 18. So we will search now in the right side. How we will search? We will just move low pointer to the mid plus 1. So we are just doing low equal to mid plus 1. Okay, so this is just example of moving a right side. Let's just take for the left side. Okay, so let's say we have a list 12, 16, 18, 56. Taking above example 12, 16, 18, and then 56 and 99. 56 and 99. Okay, so our low is pointing to the zeroth index, high is pointing to the last index. Let's do indexing 0, 1, 2, 3, and 4. Okay, find mid. So mid will come here. Okay, this is mid. Okay, so this is mid. Now let's take a target element. Target is let's say 12. Okay, now your mid value is 18 and target is 12. This is target. Okay, now as you can see, 18 is greater. 18 is greater. That means whatever the its left, whatever the its right half always contain greater than or equal to 18. As you can see, 18, 56, 99 always contain greater than or equal to 18. That means our target value, if present in this list, then it will present on the left side, is this side. This is the left half. Okay, so how we will reduce the search space to left half? Just taking the pointer, high pointer to the mid minus 1. So it will be high equal to mid minus 1. So this is the thing. Now your array look like this, something like this. A equal to, what was the values? 12, 16, 18, and then 56 or 99. 56 or 99. Okay. So let's do indexing 0, 1, 2, 3, and 4. Okay. So this is low, this is high, and our mid will be this. And we will find that we have to move, we have to cancel out this right half. half how we are going to do, like point uh, take out the high pointer to the this. So my high pointer is now pointing to the index 1. Now this is your search space reduces to this thing. Now you can just apply again, find the mid value, compare it with target, and reduce one of its half. Okay, so the binary search is only applicable for a sorted list, so you can't apply the binary search on unsorted. As you can see, whenever we are finding the mid value, it is always that its left half sorted and the right half is also sorted. So we are just eliminating one of the half and reducing the search space. Okay, so let's just write the pseudocode for it, and then we will discuss the time complexity as well. So let's do that. Okay, what we have to do, let's say we have given an array, let's call it array. Okay, and the target element. Okay, so let's call it binary. Okay, so we have to write pseudocode. So let's start. Okay, so we have to, okay, one more thing, when you will stop, let's just say you have two elements are there, let's say 12 and 16. Only two elements are there, 0, 1, and your low is pointing to this, high is pointing to this. Okay, now let's calculate the mid value. What will be the mid value? 0 plus 1 divided by 2, that is 1 divided by 2, that is 0. So my mm, mid is pointing to this one. Now let's say target is 1. Okay, now comparing this thing, all the left right right half, it contains greater than or equal to 12. So our target is 1, so we will just eliminate this right half, and by eliminating right half means I'm moving my high pointer to the mid minus 1, so my high is pointing to this and low keeps as it is. Now as you can see, my high becomes lesser than low. So high become less than low, which is, in this case, it's invalid. So this is the condition we have to stop here. So let's just erase this thing. Okay, So let's initialize low equal to 0 and high equal to n minus 1. Okay, while my low is less than or equal to high. Okay, now we will always calculate the mid. So mid will be what would be mid? Low plus high divided by 2. This is the mid. Now we will compare. If my array of mid equal to target, if this is the case, then I'll just return true. Okay. If it is not, else array of mid. Okay. So else if my array of mid is less than target, what we have to do? So we have already considered this case, like if my this thing, if my this is mid value, this is the mid value, and this is the target. Target is greater. That means what we have to do? Then we have to move my low pointer to the mid plus 1. Do nothing, just low equal to mid plus 1. That's it. Else there is one case left. That means my array is left. So let me write this. Else if array of mid is greater than my target, okay, then what we will do? Move the high pointer to the mid minus 1. So this is the code. And high if my high becomes greater, if my high becomes lesser than low, then this loops break. And if the return statement not executed, then we will return here false. Why? Because we didn't find any element which is equal to target. So this is the binary search pseudocode. Uh, it's very simple. What we are just doing, we will just iterate every time uh, while my low is less than or equal to high, which is this thing, and we will always calculate mid, low plus high. If my and remember one thing, we will always compare mid value to the target element, and if the target element is equal, then we will return true. Then we will compare, because we have two half which is sorted, we will compare mid value to the target. If my mid value is less than the target, that means we have to eliminate the left half and search the target element to the right half. Okay, so for that I'll just do left low equal to mid plus 1, and for the uh, remaining part we will just high equal to mid plus 1. Okay, so this is the pseudocodes. Let's discuss the time complexity. As you can see, every time we will reduce the half of its portion, like let's say 4, 6, 8, 9, 10, 12. So this is the list we have given, which is sorted. Now let's say 0, 1, 2, 3, 4, 5, 5. Okay, 6, n equal to 6 is given. So every time what we will do, like it's either its left part is eliminated or its right part is eliminated. Let's say this is left part is eliminated. So we will search in 9, 10, 12. Okay. Now we will again eliminate the left half, sorry, left or right, either you can. Okay, let's just say eliminating its right half. So we will 9 and 10, we will have 9 or 10. Then we will again separate it. So we will, let's say 10. So this is the element we are targeting, like we have to find target equal to 10, then we will return this element. Okay, so as you can see, every time we will divide the number of elements into two parts. Let's say initial size is n, so we will divide it n by 2, n by 2. Okay, now we will further divide by n by 2, so it will be n by 2 to the power 2. Okay, so again 2 to the power 2. Now let's say we will divide this again, so it will be n 2 raised to the power 3 and divided by 2 raised to the power 3 again, and so on, and 2 raised to the power let's say it will be 4, become 4, I think. Yeah, n raised to the power 2 raised to the power 4. So how, when we will stop, let's say n raised to the power 2, n divided by 2 raised to the power x will become 1. Okay, so then we will stop, then n equal to 2 raised to the power x, so we have to find x, so we will take log of base to n equal to log of base to 2 raised to the power x. So x will here multiplication, in multiplication, so it will be log of 2n x into log of 2 of 2, and this will become 1, so x equal to log of 2 n. So this is the time complexity, like what time complexity it will take to reach uh, the element present in this is 1, so it will be big O of log n. Okay, so this is better, like in a linear search, what the time complexity it will taking, like big O of n, and the binary search will taking log of uh, 2n, base 2n. So this is the far better. Okay, binary search is far better than the uh, linear time complexity. So this is it. I hope this video very helpful for understanding the binary search. So I have completed binary search, sorry, linear search, binary search, and pseudocode, and time complexity as well. So thank you for watching.